Okay, so thank you everyone for coming to my presentation. Today's talk is boot verification in Android to ensure the integrity of OS and partitions. Let me introduce myself first. I'm Prashant Pol, an Android engineer at Line. I basically work for a multi-device experience team. My team works especially for the login and authentication related part. This is agenda for today's topic. First, we'll see why the boot verification is significant. Then we'll see its concept, some basic one, how the verification sequence happens, how the verification happens in AB device update, that means OTA update, what is the rollback protection, and at the end, we'll see the latest version, that is verified boot 2.0 version. So the first question comes, why boot verification is significant? All of us are using the Android phone, which is having the Android OS, and for security purpose, we use antivirus software, anti-malware software, or we are having the Google Play Protect, which by default does the periodic scans, and if there is any potential harmful application, then that notifies to the user. But what if your device is having some process which is having the root permission, then that particular process may disable or they can fool this antivirus and anti-malware softwares. Or there might be a case where your system gets tampered or will have an issues before loading an Android OS. If it is compromised before loading the Android OS, then also that may disable or fool antivirus or anti-malware software. This creates a need to verify that the Android system has been booted with the legitimate content and nothing was compromised before that. So verification at the Android boot level is called as an Android verified boot or Android boot verification. What if we don't have the Android boot verification? There could be a security vulnerabilities issues where malicious actors can modify bootloader to install some spywares or malwares, and which might cause the privacy related issues. There could be an unverified firmware updates where without boot verification, there is no guarantee that the firmware which you are installing is from a legitimate source or whether it's secure or not. There could be a chance of data breach where those malwares which are present on your device, they can cause a data leaks. And the last one is a lack of trust. This is the after effect of all the first three. A user which is having a question about the integrity of the Android device which they are using, they definitely cannot use their device for mobile banking or some shopping related things or handling the corporate data because they itself don't know whether their device is secure or not. So this creates the need for the boot verification. So when we talk about boot verification, there are two terms comes, what is a boot and how the verification being done over there. So first we'll see what is a boot. So when we turn on the device, at that time the device doesn't know what to do, so it loads some piece of software which is stored at some pre-known location, and that piece of software later loads the next piece of software that will load the next piece of software, and at the end you will see Android Launcher UI. So we need to make ensure that all these piece of softwares in between doesn't have any security issues or they are not compromised. So let's see that in a bit detail. So when you press the turn on button, first you will see a boot ROM will be initialized, and boot ROM will initialize the device hardware. It scans until it finds the boot code, file system, and Linux kernel. Once it finds the boot code, it will start loading the boot code. It will start the boot sequence, and execution will be handed over to the bootloader. Bootloader will be copied into the internal RAM, and bootloader, it will load an Android OS, it will load Linux kernel, and it provides the access to fast boot and recovery mode. Later, Linux kernel will be in the process, and it's responsible for process management and memory management related things. Kernel loads the root file system, and it will search for the init process to start. So for that purpose, it will read the init.rc file and start the init process. So in any Android device, init process is the very first process which is present, And this particular init process later starts all other processes here onwards. So init process, later it will start the zygote process, which is, we all know that zygote process is the parent for all the applications, all the processes of the applications that we install on Android device. And later it will start system server, which is responsible for different things like activity manager or network manager related stuff. And at the end, we will see Android launcher UI. So this is all about the Android boot system. Then what's the Android boot verification? In simple terms, it ensures that all the code executed during the boot up was from a legitimate source, from a trusted source, and nothing was compromised in between. So is it something new? Then not at all. It's not new. It got introduced in Android KitKat version, that is 4.4. That was almost a decade ago, I guess, and maybe 2014 or somewhere, where the boot verification was first got introduced with the DM Verity kernel support. Boot verification was happening to the users, but it wasn't that much strict. I mean, if it detects some kind of tampering, then it was allowing to the boot. It was not preventing the boot. It was just showing a warning to the users. But from Android 7.0, things become a bit stricter, where boot prevention started happening. And later in Android 8.0, Android verified boot, that is the next version, which we can also call as verified boot 2.0, came into the picture. It basically standardizes everything. It introduced the partition, footer standardization, and many different things was happen, about which we will talk a bit later. And Android verified boot made things more simpler. So in a boot verification, basically it's a full source of trust, right from the root of trust to the bootloader, to the boot partition, and other partition. These other partitions could be a vendor partition or system partition, OEM partition, different things. So first thing first, what is the root of trust? So it's the foundation for all the secure operations. So it is the first thing which we can trust, so that the things which will be happening here onwards will totally depend on this root of trust. It should be designed in such a way that it should be inherently trusted in a Android perspective or in a software perspective. Generally, we used to have a cryptographic key pair, where the private key is with the manufacturer, public key is stored on the device in a read-only memory, or it's burned on the device. And the manufacturer will release a new OS version with the key which is having to them, which is a private key. And later, at the Android OS level, the OS image will be checked. It will be verified with the public key. So same key is used for the future version updates as well. The hardware protected root of trust is considered to be the most secure one. In this case, generally it's been burned on the processor chip or on a system on chip. There are some cases where user wish to install their own user install custom root of trust, but there is a guideline provided. If you wish to use your own root of trust, then you need to store that in a tamper evident storage. When I say a tamper evident storage, it's not a read-only memory. You can definitely write it, but the write process should be detected. That means you can write it, but by using the hashing mechanism, you should be detected whether it's been modified or not. And definitely the warning should be provided to the user, so that user know that this particular device is being booted with the custom root of trust and not the one created by the manufacturer. Here the user's physical confirmation is required. We cannot show just to flash the pop-up and just close it. User need to confirm that. But the question comes, why? Why somebody needs a custom root of trust? So about that, let's see a bit later. We are having the original OS where, so the device which we are having the original OS, it is approved by the manufacturer. It's being signed with the manufacturer's root of trust, and where definitely the boot verification is applied. But what if somebody wish to install their custom OS version? In that case, they need to have the custom root of trust. So with the custom root of trust, the boot verification is relaxed. You can like optionally have or have not it. But the question comes how the bootloader knows whether the device is being booted with the original OS or a custom OS. So there has to be some state which is defined into the Android to know for the bootloader whether it's a custom OS or whether it's the original OS. So this state is called as a device state. Based on whether the device has original OS version or custom OS version, this device state has been defined. This state helps bootloader to know whether it's a original or a custom OS. So there are two states, locked, unlocked. Locked, as it says, it prevents the flashing of the custom OS version and checks and warns during the boot up. On the other hand, unlocked device state, you can flash the custom OS version after making it to unlock, and in this case the boot checks are a bit relaxed. If you have to change from lock state to the unlock state, then you go to the developer option in a system setting and turn on the OEM unlocking. This particular menu is not available on the Android devices, but for the OEM devices only this option is available, and then you need to execute fastboot flashing unlock command. When you do that, then physical interaction is required with the user. User need to allow that. User data partition will be wiped out. This data partition is responsible for having all the application which user installs from the Play Store. Then RAM will be reset and user can flash a new custom OS here onwards. What if you wish to revert it from unlocked to locked, execute this command, fastboot flashing lock command, and then in developer options, optionally you can turn off the OEM unlocking menu. After this, you cannot flash any custom OS image on the device. Device will definitely be reset, and this is guided during the reselling, so that like when you wish to resell a device, it's being told that better to change the state to the locked, so that the next buyer won't have any issues, any security related issues. So these are earlier slides. In this we have seen root of trust, what is a bootloader and how does it work. Then now let's say turn for the boot partition, other partitions. But what is partitions? So boot process involves the different partitions. The different binaries or kernel images are distributed among the different partitions depending on its usability or on different parameters. Here are few partitions I have listed here. These are not all. There are many partitions in Android, but these are few which I thought to list it here. First is a boot partition, which is having the kernel image. System partition, Android framework goes here. A recovery partition, it is used for storing the image during the OTA, that is over the air update, about which we will see a bit later. User data partition, as we had seen earlier, user install application goes into this particular partition, and the vendor partition, it totally depends on the vendor, and vendor specific binaries which are not distributable with the Android open source goes into these partitions. So there are some pre-installed applications in any Android devices, or especially for the vendor specific one, which you cannot uninstall. All these applications goes to vendor related partition. Okay, so many partitions do exist in a device. Boot verification doesn't only mean verification of the boot partition, but we need to verify all the other partitions which are being referred from the bootloader. So instead, so while verifying every partition, there is a hash needs to be calculated, and it needs to be stored before delivering the device to the start or end of the partition. And then while loading the OS or while booting, this particular hash is being cross-verified. There are some partitions like boot partitions and DTBO. They are literally a small partitions, and it can be loaded entirely into the RAM, and the hash can be calculated easily, no issue with that. But there are few partitions like system partitions or vendor partitions. These are literally a big partitions. You cannot load entirely into the RAM. Even if you can load, then also it may cause a lot of device power to calculate the hash. So all these big partitions, question comes how to calculate the hash of these big partitions without consuming much power. So for that purpose, we use the tree hashing mechanism. Big partitions are read from the disk and parallelly the hash is being calculated. On the left hand side, you can see the partition data in bytes. We use some random sort, do some processing, partition hash, single hash will be calculated. This sum processing is called as a tree hashing. So let's see that in detail. So big partitions are read from the disk, and parallelly it's being divided into the 4K size, and then the hash of each 4K block will be calculated and append these hashes next to each other and then create a different layer. So definitely the next layer will have a much smaller size compared to the layer 1, because it's just having a single hash of each 4K block. So after creating the layer 2, again divide it into the 4K block and calculate the hash of each 4K block. Keep on repeating this process unless and until you will come across a single 4K block. There are some cases where the last 4K block is incomplete. In that case, you can just pad it with the 0, and then the hash will be calculated. And at the end, the single 4K block hash will be created, and we call it as a root hash. So here a tree mechanism is being used. Therefore, this technique is called as a tree hashing. So in a mapping table, we keep the root hash, the random sort which we talked earlier, and this entire mapping table will be signed with the root of trust and is being stored on the device. So during the boot up, first the mapping table is being checked whether it's being signed with the proper signature or not. If it is, then the partition verification will start happening. So in our agenda, the next is a verification sequence. So right from the root of trust, boot will be started. As we have seen, some piece of software will be loaded. It will load the next piece of software. But before handling the execution to the next piece of software, we need to verify that the next piece of software is legitimate or not. So for that purpose, we calculate the hash of the next code to be executed and then compare it with the pre-calculated hash. And if the hash comparison is successful, then repeat this process unless you finish all the piece of software, that means all the partitions and other data which you wish to verify. And at the end, the boot process will be finished. If something bad happens in between, then verification error will be generated. So after start, if something bad happens during the boot up, then user handling is required. Some pop-up will be shown to user. User need to work on that, and basically user handling is required there. If something bad happens during the runtime, while partition verification or after that, then a flag will be set, which we call as a EIO flag. It's called as an error IO flag, and a bootloader was told to restart the device. So after restarting, bootloader will check whether the EIO flag is there or not. If the flag is there, then it will enter into the EIO mode. We'll see about it. And if nothing bad happens, then OS will be loaded successfully. So let's recap everything which we had seen in last couple of slides. So when you turn on the device, first bootloader will check whether the device is locked or unlocked, irrespective of the result, and it will check whether the OS image is valid or not. If it is having any issue or if it is not valid, then you cannot boot basically. If the device state is unlocked, that means custom OS, and even if the OS image is valid, then it will warn the user about the device state is unlocked. So the OS version which you are using might be a risky one. So warning will be shown to the user, and user need to handle that. Later, in both the cases, EIO mode will be checked, whether the system is being booted with the EIO mode or not. If it is in EIO mode, then show the EIO specific screen. Here the system updater is allowed, and you can update, if new firmware or new OS image is available, then you can download that, so that if there is any issue with the firmware or the OS image, it will get resolved. And if everything goes well, then boot OS will be finished successfully. Next is a verification in AB device updates, that's over the air update. So OTA, that is over the air update, can happen when user using the device. So there are multiple slots on the device, let's say slot A and slot B, and in which slot B is in use, that means user is using an Android device with the OS image which is being stored on a slot B. At that time, slot A is the idle one, and if we need to install a new OS image, then it will be installed in slot A, and slot B is unaffected. And once the image will be downloaded successfully, device will be booted successfully, and then the swapping happens, and you can continue using the slot A successfully, where slot B goes on an idle state. So for all this purpose, update engine daemon does all these things, with like downloading the new OS version or new firmware version, and then telling the bootloader to load from the different slot. Then bootloader try to load. If something bad happens, then particular flags will be saved. So all these things are being managed by this update engine daemon. And this installation is a streamed installation. That means the entire image won't get downloaded and saved all at once. It will be done in a chunk wise, so that in between, if the network goes off, then also no issues, and your update or download goes on parallelly when you are using the device. So this is a bit in detail. Suppose we are having the two slots, slot A, B. We are using the slot B, which is active. Another one is passive. If there is an OTA update engine will check, and if it will download to the slot A, you can do this process manually from the system and check for updates, or it can be done automatically as well. If there is any problem while downloading the new OS image, then in case of failure, anyways you are using from slot B, so user experience is not affected and you can continue using slot B as it is. But if it is successful, then is bootable flag will be updated by the update engine daemon using the boot HAL, hardware abstraction layer. This particular flag will be updated, and it will tell the bootloader to load from the slot A. Okay, then bootloader will be trying to load from slot A. In between, if some boot verification problem happens, then anyways you are having the fallback as a slot B, and device will be booted from the slot B, and user can use the slot B as it is. But if it is successful, then is active flag will be updated. Again, this will be done by update engine daemon. So after that, the device state will be active, but it's not yet successful, and later user data space it will update the is successful flag to true. So once the device state will be changed to is successful to true, then from here onwards, always the slot A will be used for the user, and slot B goes into idle state. So next part is a rollback protection. We are having whatever we have seen earlier. We are having an Android phone which is having some OS signed with some key. If we find some another OS version which is also signed with the key, then we allow it to install, right? But shall we only check the keys? What if the installed OS version is having the higher version and the new OS is having the lower version? Abuser might make use of it to make the user to install the OS, like older vulnerable OS versions, and then they can stop the updates completely, and here onwards user will keep on having the older vulnerable OS versions. In this case, user's device will be at risk. So key should not be the only thing which should be checked, but along that we should store versioning as well. So install version is called as a rollback index, and a prevention from going from the new version to the older version is called as a rollback protection, and it's really important. Next is a verified boot 2.0. In a history page, we had seen this also called as an Android verified boot, which got introduced in Android 8.0, and it's basically standardized the partition footer for this purpose. It introduced the VB meta struct. This is a structural thing got introduced by the Android verified boot. It's a central data structure. It's having the rollback indexes involved in it. It's having the hash of the boot, hash tree metadata of the system partition, vendor partitions, and all these things are being signed with the key. If you are having the chain partitions, in that case, different keys might be used and different VB meta structures might be used. In some devices, VB meta different partition is present, like VB meta underscore Google. So this particular partition is having all the metadata of all the VB meta structures present for all the partitions. So there is a support for the chain partition as well. So all these VB meta partitions, you can create a hash of all these VB meta structs, and it will be called as a digest. So earlier we had seen tree hashing. Similarly, different partitions, different VB meta structs can be hashed together, and we call it as a digest, VB meta digest. And this particular digest can be used for the authenticity check or for the cross verification. And digest and keys from the hardware backed attestation data is being used for that. So in a user space, like we had seen during the boot, there was many checks are being happened, but later application or user should know whether the boot was successful or not. For that purpose, there are like certain things. There are some system properties in a kernel feature, which like a ro.android.boot, which you can use to know whether the boot was verified or not. Or on the other side, you can get the data from the hardware attestation data, and there is a enum called as a verified boot state, which is having few values. Verified, that means full chain of trust has been established with the manufacturer's certificates, which is embedded in the read-only memory. Second one is a self-signed one, where the boot partition was signed by the user's custom root of trust or custom signatures. Third one is a unverified case where a device can be used freely and verification was not checked at all. So user is responsible for its integrity and everything. And the last one is a fail, where the verification got failed. So as a conclusion, boot verification is really important to trust the device. If the boot was compromised, then any additional security application which you are having into the OS is of not much use. And cryptographic hashing and signing is used to ensure the authenticity of the executed code. And after the boot up, hardware back key attestation data could be used in the user space to decide whether the boot verification was successful or not. So these are few references. There were many more. Thank you. That's all.